Hello, and welcome to our, last lecture on chi-square. Let's get it cracking. So chi-square tests are non-parametric tests, and I'll go a little more into those as we go forward in this lecture. Just so you know, though, I want you guys to let me know what you want to be in the final in-class activity, because that is coming up. So be sure to let me know. I already have a final in-class activity prepared, but since the final will be cumulative, I tried to make sure that last activity has a fair mix of the material we've covered up to this point in class, which is essentially all of it. So with chi-square, it is spelled C-H-I, but is pronounced chi. So we'll have our boys from Instinct remind us that it is not baby chai, 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 or baby chi, chi, chi. It is in fact baby kai, kai, kai. You may hate me, but it ain't no lie. Baby, it's kai, kai, kai. So chi-square tests, as I mentioned, are non-parametric. That means that the variables that are involved in these sort of tests are usually nominal or ordinal variables. Essentially, they're categorical. If we can remember way back in the day, nominal variables are essentially providing names to things. So you can use numbers, but the numbers don't really mean anything. So for example, your social security number, it could start with 702 or 555 or whatever, but one social security number, if it's greater than another, doesn't really mean much. So essentially, though, I'm boiling it down to chi-square tests are using categorical variables exclusively, as opposed to parametric tests, which we have used. We've been doing them all the way up to this point. They use ratio or interval variables. So essentially it boils down to chi-square uses exclusively categorical variables, whereas parametric tests can include quantitative variables. So with parametric tests, we had our one sample Z and T test back in the day. So we're comparing the mean of a sample to the mean of a separate sample of a separate population. With an independent samples t-test, we're comparing the mean of one independent sample to the mean of another. Dependent, we're comparing the mean difference between two dependent samples. With ANOVA, an analysis of variance, we're comparing the differences in variance between three or more groups. And then correlation, we're looking at the relationship between two quantitative variables. Well, with everything we've gone up to this point, it has some quantitative variable mixed in. You know, we're looking at a mean, which is a quantitative measure, or variability through use of variance or standard deviation. All of these are quantitative measures of variables. They're, you know, we can't take the mean of the color blue or what have you. It's just, these are numbers, quantitative variables we're working with. But this is not the case with chi-square. As I mentioned, it is strictly categorical variables that we're working with. So we don't really have to worry about means and variance or standard deviation or any of that. It's more so we're looking at counts with non-parametric tests, with chi-square tests. So with these types of tests, with non-parametric tests, data does not need to be normally distributed. So I know some of our assumptions for, let's say, an independent samples t-test was that the population in which we obtained this data from had to be normally distributed. Not the case with non-parametric tests. This is used, as I said many times up to this point, we are using categorical variables when we're looking at non-parametric tests, and categorical variables only. It's not a mixture of, like how we had independent samples t-tests. We had, oh, you know, we're going to compare one group who had a study guide and one group who didn't. Well, that's a categorical variable. We have two separate categories in which people are in, but we compared them on their mean test scores. Well, we're not comparing any means or standard deviations or any of that sort when we're looking at chi-square tests. It's essentially counting frequencies within the conditions of the categorical variables. So I mentioned, I believe, like, oh God, long time ago when we talked about categorical and quantitative variables, that, you know, we can find the mean for quantitative variables. I can ask how old everyone is in the class. You provide me your age, and I can calculate the mean of everyone in the class, the mean age. I ask how many people have blue eyes, brown eyes, green eyes, or any other color eyes, and I can't find the mean of blue eyes or brown eyes. It's just I count how many of those there are. Oh, there's 20 brown-eyed people, 10 blue-eyed, or what have you. It doesn't really work as how I find the average of blue-eyed people. It's just there are 10 in the class. Same thing with chi-square tests. We're going to be counting the frequencies within the conditions of these categorical variables. So as an example, we have to start a chi-square goodness of fit test. Now this is looking at only one categorical variable that has 2 or possibly more conditions or levels. So if you get confused, we have goodness of fit has one categorical variable, and then later we'll discuss chi-square test for independence that has 2 categorical variables. But just to kind of keep it in mind, goodness of fit, when I think of goodness of fit, I think of how well my clothes fit me, like a pair of jeans or this jacket because I'm cold. I don't really think about other people. I don't really care how my jacket fits other people when I'm trying to think of if I should wear it or if I should continue wearing it. Maybe I need to, get it out of my circulation because it doesn't fit anymore or what have you. Goodness of fit, one categorical variable. So my jacket, I am the only person who wears it. I am the only person that I'm concerned that it fits because it's my jacket. I am one categorical variable. Now I don't know, that kind of helps for me, but if it doesn't, feel free to think of other examples or little heuristics to help you remember that goodness of fit chi-square tests only have one categorical variable. Now it can have multiple conditions. So for example, we can have the categorical variable of eye color, and it can have blue and brown, which are pretty standard, but it can have more than 2 conditions or levels. It could have, blue, brown, green, purple, red if you're Satan, I don't know. But you could have more than 2 conditions, but the key is there's still one categorical variable of eye color. So as an example, a different example, I should say. So here we have a chi-square goodness of fit test where we asked 80 people if they're going to be, or if they had recently participated in Black Friday or Cyber Monday shopping. So essentially just spending your money after Thanksgiving. So our question essentially was, did you shop on Black Friday or Cyber Monday, yes or no? So we have our categorical variable of did you shop, and our conditions being yes or no. So when we have these 80 people that we asked, 63 said yes, they did shop on Black Friday and or Cyber Monday, and 17 people said no, I did not shop on Black Friday and or Cyber Monday. So, I mean, that's our observed frequencies. We had 80 people and we just pretty much tallied up which ones did and didn't shop, and that is what we have so far. But what makes it a test? Obviously, there's going to be a little more complexities than just asking people if they shop, putting it at a table, and then saying, hey, my chi-square goodness of fit test is done. No, obviously not. Come on now. But the purpose of these tests, the purpose of a goodness of fit test, is to observe how well, or examine how well our set of observed frequencies, aka those 80 people we just asked, did you or did you not shop on Cyber Monday / Black Friday, how well that data that we collected fits with what's expected. So a lot of times when it comes to what's expected, the problem itself provides that answer to us. So if I were to just simply say, oh, how many did I expect? What percentage of the population of the United States did and did not shop on Black Friday, Cyber Monday? I don't really have an answer. I have an estimation, but oftentimes the expectations that we're looking to see if our observations fit are provided in the example itself. So that's what the next slide is going to be about. Same problem, or at least our same observed frequencies of the same amount of people saying yes and no to shopping. But now we have a little more information. So here we go, surveyed 80 people, we already knew that. Asked them if they participated in any Cyber Monday / Black Friday shopping, we knew that. 63 said they did, 17 said they didn't. That was from the 2 slides ago, so that all the same. However, Now that we're going to have more information to where we can actually calculate a chi-square goodness of fit test, and that is this next sentence here. Based on the population data of the United States, it's estimated that 24% did participate in holiday shopping and 76% did not. So our goal now is to see how well do our observed frequencies, our data that we collected, how well does that fit with this idea that 24% said they did not, or they did, excuse me, and 76 said they did not. So here we are. So we have to calculate the frequencies expected. So we have the percentage of 24 and 76, but in terms of, okay, so we have to kind of put that more in the context of our sample. So if 24% of the expected population is saying that they did shop and 76 are saying they did not, we have to fit those to our sample to see, okay, out of 80 people using these expected values of 24% did and 76 did not, how many people will we expect to see in our sample of 80 if this were the case? So we just multiply 80, our total sample size, by the two percentages. So by 24 or 0.24, 19 is 80 times 0.24. So 19 would be the, yes, I did shop. That's the expected value out of 80 people. If 24% and 76% for yes and no shopping respectively were true, or if our data did fit that, we'd expect to see 19 said they did not and 61 said they did, or damn it, I keep saying that backwards. 19 said they did and 61 said they did not. Well, obviously we know that's not the case. However, we have to continue on because while we know, hey, we did not have the expected values, there's actually quite a big, difference in these two. We do have to kind of go a little further and state our hypotheses and all that jazz. So the null hypothesis is saying that the distribution of proportions is the same as expected. So the percentage of people who did shop is 0.24 and those who did not shop is 0.76. Our alternative hypothesis states that the distribution of proportions differs than that stated in the null hypothesis, or it's different than the expected values. So essentially, the null hypothesis is saying that our data matches that of what is expected or what's been stated in the question, as we can see, and our alternative hypothesis is saying, hey, it's different. Our data does not match the expected values. Oops. So we have to, step 2, set the criteria. And as per usual, part of setting the criteria in step 2 is knowing that what our alpha value is. And so often is that alpha value 0.05 or 5%. So we're just going to leave that there. Now we do need to consult the chi-square table in order to give us the critical chi value. To do this, we have to do degrees of freedom, which is essentially similar to how we did before, where it's the number of groups minus 1. So K, as we remembered from ANOVA, K is the letter that represents number of groups minus 1. So we have 2 groups. Again, this is not 2 categorical variables. This is 2 conditions or groups of our categorical variables. So we have the did and did not shop, the yes or no for did you shop or what have you. So we had 2 groups. You can either say yes or no. And 2 minus 1 is 1. So our degrees of freedom is 1. Now looking at the chi-square table, with degrees of freedom of 1 and alpha set at 0.05. I posted this on Canvas so you can see this if you want to also consult the chi-square table on your own time. But indeed, our critical value is 3.84. So now we calculate the test statistics. So in order to do this, that X looking notation here for X2 obtained, that's actually the chi. So chi-square obtained value equals the sum of the of each of the observed frequencies minus the expected frequency squared divided by the expected frequency. Now keep in mind the observed frequencies, or FO, is what we actually gathered. So that is when we asked the question, did you shop on Black Friday, yes or no? What we gathered with our sample. The expected frequencies is what the problem provides. Oh, in the United States population, 24% did shop and 76 did not. Well, that's expected. Observed is always going to be what we actually gathered. Expected is what the problem typically provides us in terms of, you know, what the population says. So let's fill this in. It's actually fairly simple. I find it a lot easier to make that table because then you can just kind of fill in the blanks. So just like for standard deviation, we have to, with that sigma, that kind of really sharpened E, we have to, you know, do the sum. So that is telling us we need to find all the observed values minus the observed frequencies, and then, or observed minus the expected frequencies, and square it. So we only have two groups here, so we only have to worry about two problems. But we have 63 for the observed frequency of yes, they did shop, minus the expected frequency of 19 squared, divided by the expected frequency, so that is 19. Now we have to do that again for our other observed value. So our 17, our no, minus 61, that's the expected number of times people would have said no, they didn't shop, squared, divided by the, again, the expected frequency of 61 yet again. So we need to have, for each box we have here, for each categorical condition we have, for each condition of the categorical variable, yes, no, we need to have 1, 2 different fractions to symbolize that. So this is the yes, this is the no. 2 fractions, 2 conditions, boom, bam. There we go. So we do this math. And 63 minus 19 squared is 44. 17 minus 61 squared is negative 44, divided by 19, divided by 61. We do all this. We have our chi-square obtained value of 133.63. So there's our test statistic. There's our chi statistic. And now we just, you know, make our decisions. So we compare our chi value to the critical chi value. So we have 133.63 is, yeah, it's greater than 3.84, that's for sure. So we would reject the null hypothesis. So this is saying that the frequency of excuse me, the frequency of people going holiday shopping was not similar to what was expected. Again, the null hypothesis states that, yeah, our data is our data matches what was expected, but it didn't, because look at how fatly we rejected that null hypothesis. It was, oh man, super reject. Anyway, so come up with some examples of different chi-square goodness of fit tests. I've already kind of come up with one with the eye color. You know, we have, ooh, you know, blue, brown, green, purple, red, Satan, etc. It's essentially just kind of thinking of, you know, categorical variables and various conditions within them. Now we get to chi-square tests for independence. Now I mentioned how we have two types. We have goodness of fit and we have tests for independence when it comes to chi-square. Now we just discussed goodness of fit, how you have one categorical variable with as many conditions as it needs. So we had just yes or no as the conditions of our categorical variable before, so that's 2 conditions. But there could certainly be more, like for the case of eye color, there are certainly more eye colors than blue and brown. So now we get into tests for independence, where now we have 2 categorical variables. They can have as many conditions as they want, but the key is that we now have, instead of 1 categorical variable like we did for goodness of fit, now tests for independence has 2 categorical variables. So we're looking, with this test, with 2 categorical variables for tests of independence, we're checking to see, are these categorical variables related, and to what extent are they related? So when it comes to variables being related, if you're wondering, well, what the hell does that look like? Well, we look at these two separate examples. So we see at this top one, we ask people, do you have depression? Yes or no. And then we measure their serotonin levels. And we put those in a categorical measurement of serotonin where they're characterized as having either low or high levels of serotonin. And of course, our depression question is quite simple. It's depression, yes, no. So we have two categorical variables of depression and serotonin levels. And each of these categorical variables has two conditions, either yes or no for the categorical variable of depression, or low and high with the categorical variable of serotonin. So we look at this and we see that, okay, for people who said, yes, I have depression, a lot of them have very low serotonin levels. And for those that say, no, I don't have depression, not a whole lot have low serotonin levels. And the opposite is true when they say, when we look at the high serotonin levels. Very low amount of people who have high serotonin levels are depressed or have depression, whereas a very high amount of people that have, wow, okay. So whereas a lot of people who do not have depression, this 90, a lot of them also have high serotonin levels. So we would say that, hey, serotonin levels are related to depression because this frequency says that for a majority of people who say, I have low serotonin levels, they are also suffering from depression, and vice versa. For people who have high serotonin levels, a vast majority of them tend not to have depression. So serotonin levels, in that case, there's a dependent relationship there. They are related. Serotonin levels in the brain and just the presence of having depression, they're related. When we think about other things, if you're looking at an independent relationship, this is saying that these things are not related whatsoever. They're independent of one another, like Beyonce from Destiny's Child. So we're looking at depression again, okay? So yes or no, do you like depression? Do you have depression, yes or no? And then we ask people their preference for either Coca-Cola or Pepsi. Well, there is not, we'll see that this is kind of a fairly, well, actually, this is a perfectly distributed chi-square table here, where 50 of the 200 people, all of them, you know, they're all evenly distributed across these four different conditions of I like Coke and I am depressed, I hate Pepsi, or, you know, I prefer Pepsi, but I do not have depression, etc. So we have everyone's evenly distributed across the board here, 50, 50, 50, 50. That's telling us that there's not really there is not a dependent relationship between your soda preference and depression. These two things are not related. And why should they be? That makes no sense. You know, if you are more privy to drink Coca-Cola, that doesn't mean you suffer from adamant depression. It's just soda preferences and your mental health typically aren't related. So they have an independent relationship. So let's take our holiday shopping example from before and tweak it a bit. So again, before we had only one categorical variable of did you shop, yes or no. So let's add another one. Let's add another categorical variable to make it a chi-square test for independence test. So do your friends like you? Again, simple answers, yes or no. So we have, now we're kind of tweaking a little bit. So now we have 85 people who said they did shop, say their friends like them. 15 people said they do not shop, and yes, their friends like them. 12 say, yes, I shop, but no, my friends don't like me. And 72 said, no, I didn't shop, and no, my friends do not like me. So let's add our rows and columns first. You'll see why this is important later on. So across the board here, 85 plus 15 is 100. So the total people saying their friends like them, yes, is 100. 12 plus 72, the total people saying their friends did not like them was 84. And the same thing for the columns as well. So 85 plus 12, total people who said they shopped for the holidays is 97, and 87 for those who said no. Now we add these together, 180 or 100 plus 84, or alternatively 97 plus 87. Either way, we have a total we have our sample size total of 184. Okay, add all these boxes together, we get 184. So now I mentioned how we have to compare observed frequencies to expected frequencies. Well, that's the same case when it comes to chi-square test for independence. However, instead of the expected frequencies being provided for us, we have to calculate our own expected frequencies for the test for independence. It's fine. It's not really that difficult. It's a little time consuming, but it's not that difficult once you have the rows and column totals and then the total sample size calculated. Why is that? Because those are the exact numbers we need for our equation. Whew. So row total times column total divided by n. Now we need to do that for each of these boxes. We don't just do it for one and then done. We need to see the total expected frequencies for yes, I shopped, yes, my friends like me, yes, I shopped, no, my friends don't like me, no, I shopped, yes, my friends like me, no, I didn't shop, no, my friends don't like me. We have to calculate the expected frequencies for all 4 of these boxes. So let's do it. So again, row total times column total. So the row total, I'm looking at yes and yes here, this top left box here. The row total is 100 times the column total of 97 divided by the n, so the total, which is 184. That gives me 52.72. Now I continue doing that. It's going to be different for each of these. So for no, I did not shop, but yes, my friends like me, 100 for the row total and 87 for the column total, divided by 184, 47.28. Go down, we have 84 for the row total for yes, I did shop, and no, my friends don't like me. 84 for that row total times 97 for the column total, divided by 184, 44.28. And then we have it again at no and no, 84 row total times 87 column total divided by the total, the n, 184 equals 39.72. So what I've done here, the previous slide has all the work involved, but now I'm just simplifying it. So we have our observed frequencies and the expected frequencies are in parentheses. So again, the observed frequencies is what we actually measured, obviously, because when I'm actually going out and, you know, asking people, I'm not going to have a 0.72 person say, yeah, I shopped. I don't even know what that looks like. But the observed frequencies, so we actually measured 85 people saying yes and yes, 15 saying no, yes, 12 saying yes and no, and 72 saying no and then no. So again, the expected frequencies we calculated prior in the previous slide, those are in those parentheses, 52.72, 47.28, 44.28, 39.72. I still have the row totals here and the column totals here, as well as the sample size, the total sample size of 184. But this is essentially moving forward what we need to know. All right, so before we start calculating the test statistic, we should probably state our hypotheses and then set the criteria first, right? Yeah. So our null hypothesis, it's a little wordy and it kind of differs based on this question, but the null hypothesis states that going holiday shopping, our first categorical variable that had the yes or no, and whether your friends like you or not, again, the second categorical variable with yes or no as the conditions, are independent, meaning they are not related. The observed frequencies will be equal to the expected frequencies in each cell. The alternative hypothesis says the opposite. Going holiday shopping and your friends liking you or not are dependent, so they are related. The observed frequencies will not be equal to the expected frequencies in each cell. Now again, we're going to use that chi-square table to set the criteria. So again, we're going to need alpha and our degrees of freedom. Alpha, 0.05. Do we even need to say it at this point? Yes, we do. Alpha is 0.05. And our degrees of freedom, to calculate degrees of freedom for a chi-square independent test for independence, it is the groups, the number of conditions in group 1 minus 1 times the number of conditions in group 2 minus 1. So that's 2 for the total conditions in did you holiday shop, yes or no, minus 1 times 2, do your friends like you, yes or no, minus 1. So multiply those two together and you get 1. So similar to our previous question, hey, our critical value is yet again 3.84. Cool. Looking at that chi-square table. Now we're going to compute the test statistic. Yes, it's the exact same formula. Woo! Except obviously now we're going to have a little more of those fractions. Like I said before, we should have a fraction for each of the conditions we had. Previously, we had only 2 conditions, the 2 conditions of our one categorical variable, except now we have another categorical variable and thus 2 more conditions. So I wonder how many fractions we're going to have. Well, we're going to have 4. Anyway, so it is the same exact formula, so that makes it easy. Now it's still kind of a nuisance to calculate, but it's still fairly straightforward. So we have 4 boxes here. We have 4 total conditions, 2 for our did you shop categorical variable and 2 for do your friends like you categorical variable. So that's telling me we should have 4 fractions here, 1 for each of the expected and observed frequency values. So we'll start with the first one, 85 minus, so our observed frequency of 85 for yes and yes, minus 52.72, so minus the observed frequency squared, divided by 52.72, the expected frequency. I believe I keep saying observed when I should say expected. My apologies. So then we'll go just over this way. So 15 for did you shop? No. Do your friends like you? Yes. 15 minus our expected frequency of 47.28 squared divided by our expected frequency of 47.28. Again, these expected frequencies we calculated by taking the product of 100, our row total, times our column total, 87, divided by 184. So if you're wondering, if you're thinking, whoa, 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 I spaced out for a second, where are these 47.28 numbers coming from? What the hell is that? Go back a couple slides, rewind the video, however many minutes. I don't know exactly how long ago I mentioned it, but you can see that we had calculated this using this information and this information, but I digress. So now we have to, again, we have to do it for each of our squares, each of our cells in our table. So we have 12 for yes, did you shop? No, my friends don't like me. So 12 minus 44.28, that expected frequency squared, divided by the expected frequency of 44.28, plus, and then lastly, 72 minus 39.72 squared, divided by 39.72. Okay. So we have the formulas laid out. So now let's just calculate it. So boom, 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 da, 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 da. Magic, magic, magic. I've already calculated these, but you know, so here we go. You know, you simplify them all, you square them, you divide them, you add them. We have the chi-square value, the obtained chi value of 91.56. Is that greater than our critical value of 3.84? You're goddamn right it is. So we're going to reject that null hypothesis again. So in this case, our chi-square test of independence showed a significant relationship between going holiday shopping and whether our friends liked us or not. So they are related, they are dependent. It is not an independent relationship here. There is indeed a dependent relationship. All right. So you can come up with categorical variables with 2 conditions in each and fill in the blanks. Do your own chi-square test. But essentially, what I want you to know is that chi-square tests deal with categorical variables exclusively. They are non-parametric tests. Chi-square goodness of fit tests only have 1 categorical variable with however many conditions it needs, whereas chi-square tests for independence has 2 categorical variables, and each of those categorical variables could have however many conditions it needs. But that concludes my discussion, my lecture series on chi-square test for independence. So thank you for making it this far. Don't forget to like and subscribe.